In the previous lecture, we saw how a charged particle can gain energy by crossing a shock front. And we saw the fractional gain in energy will be in the order of u by c, where u is the velocity of the shock, and this is a first order. So that's why this type of acceleration is called as a first order Fermi acceleration. And since it's first order, and if you remember the earlier stochastic acceleration process where the fractional energy gain goes as v by c whole square, so that is a second order, so this is a first order, so therefore this acceleration, the acceleration at the shock front, is going to be much more efficient than the acceleration happening at the by the stochastically random moving meters. So in this lecture, we will look at what will be the typical accelerated electron distribution at the shock front. So to start, and interestingly, if you remember in the acceleration, stochastic acceleration, every scattering is going to impart a change in the momentum of the particle, change in the energy of the particle. When we come to shock acceleration, doesn't matter, because the energy change due to the scattering by the inhomogeneities are negligible compared to the energy gain, which by the crossing the shock front. So the maximum energy is by the crossing the shock front rather than by the individual scatterings. So I don't really have to consider the diffusion of particle in the region. Rather, I'll say the number of times it crosses the shock front, it is going to accelerate. So I don't want to really complicate with the diffusion equation, momentum diffusion equation and all. Rather, I can simplify this whole process as something called as the acceleration rate. I'm going to call, if dE by dt is the rate of acceleration, so I can define the entire acceleration process as some sort of rate of acceleration, which is defined by the number of times it is going to cross the shock front. I will parameterize in terms of some time scale, say something like a TACC. So that means, this means it's going to, if we take E, that means ln of E will be equal to T by TACC. So E means energy gain will go as exponential with TACC. Fine. So then the evolution of the particle distribution, I can write it as del n by del t, which is the evolution of the particle distribution. The particle is going to have particle will be, n is the number of particle density, whatever you call, and it will be a function of energy and time. And this is going to face an acceleration term that is defined by this. So that will be del by del E of dE by dt of n, right? So this defines the gain, particle energy gain in the gained by the shock, gain at the shock front, and this should be equal to the injection. The particle has to be injected into the accelerator, the shock front. So let us, for simplicity, let us assume a monoenergetic. It's a very low energy. Some low energy particle are being at both the side of the fluid, that's the upstream and the downstream. So I'm going to consider that as a monoenergetic, so that let it be Q0, some delta function of E minus E0. So, and where this is the injection rate, and then here it is not, the particle will not be always being tied at the shock front. After a certain time, they can, once they cross here, now they have to scatter back and reach this upstream region. So, but it is not always there. There's always a probability the particle can move out of the, move down into the downstream region, can never return back. So that means the particle can lose, it physically can lose away from the shock front. So there is a loss of, particle loss also. I'm going to call, again I'm going to parameterize that in terms of a time scale. This is a physical loss of the particle. So that I will, it's a loss, so that is injection minus n by, I'm going to call that as an escape time scale. The typical time scale at which the particle can leave the system. Fine, so let us try to solve this equation. So, and we said dE by dt for acceleration, I'm going to write it as n of E by TACC. NE by TACC. So now, if I consider steady state, so then this guy goes to 0. So then our equation will be d by dE of E by TACC, that's the acceleration time scale, into n equal to Q0 delta of E minus E0 minus n by t escape. So now we want to look at the spectrum, the accelerated spectrum, that is the energy which is greater than E. So what the spectrum will look like beyond E0. That E0 is the injection energy. So I'm going to look for an energy range which is E is greater than E0. So in that case I can neglect this term. So what am I going to get is d by dE of E by TACC n will be equal to minus n by t escape. So let me open up. So this is going to be well, n by TACC and plus E by TACC into dN by dE. So let me write it down here. So this is okay. So this is going to be minus n by t escape. So let me take out the TACC, divide by TACC on both the sides. So this is going to become n plus E dN by dE equal to minus TACC by t escape to n. Cool. So let me take this n here. So this is going to become n minus n, or I can write this equation as E dN by dE is equal to, let me take the minus n commonly outside. So if I take minus n commonly outside, so this is going to become 1 plus TACC by t escape. 1 plus TACC by t escape. Well, this is simple. So I can always take this one as a dN by n equal to minus dE by E into 1 plus TACC by t escape. Remember, there's an assumption we said. We had assumption this acceleration time scales and escape time scales we are considering to be a constant, but in general they can have an energy dependence. So for a simplistic approach, we are considering to be a constant. Fine. So then the solution, this will be, so you can write this will be log of n, this will be log of E. So and therefore this guy therefore this goes as, therefore n will go as e to the power of minus 1 plus TACC by t escape. So that is the power law. What is the power law? So that means the accelerated electron distribution is going to be a power law electron, and that will be, the shape will be something like, if I plot log of E here and log of n here, this is going to be a straight line with the slope, negative slope, where the slope is equal to 1 plus TACC by t escape. That will be like this. And the slope will be minus 1 plus TACC by t escape. If you remember, we also got for the stochastic acceleration also, the final solution, if you go back to the lecture and if you see, the final solution is again a power law, and there was an index, and there also we defined an acceleration time scale based on the momentum diffusion term, and we also had an escape time scale, that's a characteristic time scale at which the particle can leave the system. So, and if you remember, there also we got an power law, and the index will be going again as TACC by t escape. This factor will be there. If you can go back and check the lecture, you will see that. And now, interestingly, there, if you remember towards the end, I put up a condition. The case when the escape time scale is infinity, because I'm having a huge plasma moving and there's a lot of magnetic inhomogeneities are moving, there can be particle can be confined in this plasma for quite long. That means the escape time scale can be infinity, can be approximated to infinity in case of a stochastic acceleration. Whereas for a shock trend, that is not the case. The particle has to be tied within the shock trend. The escape time scale, I can't consider the escape time scale as infinity. Escape time scale will be always a finite. It has to be always tied within that. So that means since the escape time scale is smaller in case of a shock acceleration, this is going to be larger. That means the shock acceleration will be always steeper. So shock acceleration can produce a steep spectra compared to a stochastic acceleration, because stochastic is at all because of the escape time scale. So, and this is a very interesting thing. So the shock acceleration, even though it is an efficient acceleration, it produces a steeper spectra. Stochastic acceleration, even though if it is not that efficient as the shock acceleration, it can produce a harder spectra. It all depends upon the escape time scale. So, and so this is what we call as a accelerated particle spectrum, and this is typically the spectrum way the spectrum looks in case of an shock acceleration. So with this, I will stop this lecture series on particle acceleration. So we had an idea what is the magnetic reconnection and how the energy particles are being gained in magnetic reconnection, and then we came down to the Fermi acceleration process. We saw stochastic acceleration, and then we saw this came down to the last topic, that is the shock acceleration, and we saw the shock acceleration goes as by V by C or U by C. So that's the first order acceleration, and that's the most efficient acceleration. This is the typically accelerated spectrum. A shock accelerated spectrum produces a steeper spectra, but a more efficient accelerator but produces a steeper spectra. A stochastic acceleration produces a harder spectra. Well, and this is how the particle acceleration of astrophysics is being understood till now. Thank you for watching all the lectures and for your patience. So maybe some other time I may come up with some other lecture series. Until then, goodbye.